All right, today's lecture is one of the last in the chapter, and this would be part 4 on covalent bonding. And this section we're going to discuss not just covalent bonds, but we're going to discuss what's called polarity. What are polar covalent bonds, and what is a polar molecule? And the two are actually different, even though they sound somewhat the same. And so we're going to kind of differentiate between one and the other. The first thing that we're going to deal with is a polar bond. And a polar bond is relatively simple. It's basically a bond between two atoms, and it's a bond where you have shared but shifted electrons. So it's a covalent bond in that they're shared. So that could be a single, double, triple bond. But these electrons are shifted, and this goes back to that trend we learned last chapter, where we talked the periodic table and the different trends, and this is the trend of electronegativity. And if you remember electronegativity, we compared to this idea of tug of war, where if we take a look here on this particular chart here, let's say this bond right here between hydrogen and oxygen, they're sharing those electrons, but they're not necessarily sharing them equally, nor are these nice little atoms, and they're willing to share with one another because they're so kind. In essence, they both want those electrons, so they're playing tug of war. They both want those electrons, and they're trying to pull those electrons towards themselves to complete their duets or their octets, as the case may be. And so in this situation, what we want to look at is which one of these two atoms, we have two atoms here playing tug of war on this pair of electrons shown in our bond here. One of them is oxygen here. Oxygen is tugging on those electrons, and the other one is our hydrogen atom. Those are the two atoms that are tugging, in this particular case, on those electrons. And what we want to look at is each one of them has a value of electronegativity, and you can find that on your periodic table, on the back side of your periodic table. And oxygen, roughly speaking, has an electronegativity of around 3.44, 3.5, depending on which chart you look at. So we'll kind of round it, and we'll say roughly speaking about 3.5 is oxygen's electronegativity. Hydrogen, on the other hand, has an electronegativity of 2.2. And so as we compare those two, you notice that oxygen has the higher number, a higher value. Higher electronegativity means it is stronger. So if you want to think of this in terms of physical strength in that tug of war, oxygen would be the bigger, stronger atom, and it would therefore pull the electrons towards itself. It would be winning that game of tug of war. And so what we're going to do in simply answering whether this is a polar bond or not is we want to compare the electronegativities, and if they are different, then those electrons are going to shift in one direction or the other. In this case, if we take all this away and kind of illustrate what's going on here, in this case, since we now know that oxygen is the strongest one, the electrons in this bond right here are going to shift towards oxygen and away from hydrogen. And so we call that, whenever there's a shifting of electrons, they still orbit around hydrogen, but they spend more time around oxygen, is the idea in a polar bond. So they are still shared between the two. They still do complete hydrogen's duet, and they still complete oxygen's octet, but they shift and they spend more time around oxygen. And as a result, we call that a polar bond. So anytime, one way to figure out whether you have a polar bond or not, and this is one of the things I will ask you on the test, is we'll have something like this, and I will ask you, how many polar bonds, or if something is a polar bond. And as you look at hydrogen and oxygen, there's a bond there. Is that a polar bond? How do I know? Well, I can look at the electronegativity between the two of them, and if it is different, then I have a polar bond. So that's really kind of the answer to that question. Is just, do I have a polar bond or not? And really, if you want to simplify it even more, for our purposes in this class, to keep it really simple, to a large degree, if you have a bond between two different elements, then you're going to have a polar bond. So, as long as my bonds are not the same, or the element is not the same. So let's say if I had hydrogen bonded to another hydrogen, well, in that case, since they have the same electronegativity or same strength, the pull on these two electrons right here in the middle would be exactly the same. And so those electrons would not shift one direction or the other. They would stay exactly right there in the middle. And so we would call that a non-polar bond. And about the only time that's going to occur, at least for our purposes in this class, just for sake of simplicity, is going to be a situation where you have two atoms of the same element bonded to each other. But if we go back here and take a look, kind of the simple way to look at it is I'm going to compare, well, where's my bond? My bond's right here, and I'm going to look at the two elements that it's between. Well, if those two elements are different elements, they're going to have different electronegativities. One of them is going to be stronger, and therefore a stronger pull on those electrons, and therefore I'm going to end up with a polar bond. So if the question was, do you have a polar bond or not, kind of the simplistic way to look at it is just look at, do I have a bond between two different elements, and if so, then it's probably going to be polar. More often than not. So that's kind of the simplistic way that we're going to explain polar bonds. Now where we're going to go next is where things get a little more complicated. And so if I go back to this, I can answer the question here, yes, I have two polar bonds. Each bond here between the hydrogens, hydrogen is weaker than oxygen, and therefore the electrons are going to shift towards oxygens. We would classify those as polar bonds. However, the next question is the molecule polar? So when we're talking about the molecule being polar, we're talking about the whole thing here, not just the little bond here. So that's the difference. We're talking about the whole thing, not just that individual bond. And that's where the difference comes in. And this is a little more difficult to answer. So here's how we go about this basically. And this is where you will need your periodic tables and to look at electronegativity. First thing that I'm going to do is I want to draw the molecule like I've got it drawn here. I want to draw that structural formula or the Lewis formula as it's written. And I want to draw it preferably in the correct shape. So we talked about shapes in last chapter. So if it's bent like this one is, I want to make sure that I draw my hydrogens in a bent shape. If it's a tetrahedral, I want to make sure and draw it in more or less a tetrahedral type shape, so on and so forth. I want to make sure that my shape is as close to accurate in a two-dimensional way as possible as I draw that, because that's going to help me in determining whether this molecule is what we call polar or not. And the next thing that I want to do is I want to examine around my central atom and figure out where my bonds are and which direction are my electrons shifting. So basically in this one, I'm going to take a look here, and I have my bond with hydrogen and oxygen, and we already said that hydrogen is weaker, oxygen is stronger, so my electrons are going to shift towards oxygen on both of these bonds. So they're going to shift towards oxygen here. And what that's going to cause is this. As those electrons shift towards oxygen, because they're spending more time around oxygen than they are hydrogen, and we said electrons are negative, oxygen's going to get a semi-negative charge over here because more electrons are going to be exposed and orbiting around the oxygen atom. On the other hand, because those electrons are shifting away, in a sense being pulled away from hydrogen, hydrogen ends up with a semi-positive charge. Now this is a little different than an ionic bond, because in an ionic bond the electron completely is removed from the atom and goes to another atom, goes away from the metal to the non-metal. In this case they're not completely removed, they're just shifting, so they're closer to oxygen and they spend more time around oxygen than they do around hydrogen. The key thing to know is this: which direction do they shift? And it's always going to be away from the weaker one and towards the stronger one. And again, if you're not sure which one is weaker or which one's stronger, you can go to your periodic table, look at the electronegativity. There's a number, there's a value for each one. We kind of talked about that last chapter. I can look at the number for each one. Whichever one has the higher number is going to be the stronger one. And so I can compare those two, and that's the one that the electrons are going to shift towards. And so that one will end up with the kind of negative value, and the other ones the ones it's shifting away from, will be positive in essence. And what I'm looking for to answer my question, is it a polar molecule or not? Polar is exactly what it sounds like. So whether you're dealing with magnets and you have poles, whatever the case might be, poles deals with opposite ends. Okay, so poles of the Earth, north and south pole, it deals with opposite ends. So as I look at my molecule, I want to see, do I end up with opposite ends? Do I end up with one end that's negative and one end that's positive because of that shifting of electrons? And as I look in this case, I do. I have a negative end right here and positive ends on the molecule here. And so this molecule is what we call polar. So I'll take that away so you can see the negatives and the positives. So I have opposite ends that are polar on this molecule. And this is going to be important a little bit later on. Right now we're just going to figure out whether the molecule is polar or not. Later on we'll come across a chapter dealing with solutions, and in that chapter we'll talk about why do certain things dissolve and other things, like for example, why does salt or sugar or something like that dissolve in water? And why does oil not dissolve in water? Why does it not mix well? And the simple answer to that is it has to do with this very concept here. If something like water is polar, it has opposite charges on the ends. It has a positive end to the water and a negative end to the water. And so as a result, other things that are polar can dissolve in it really well because they can interact with those charges. Things that are nonpolar, like oil, don't mix in because they can't react with those charges. And we'll kind of go into more of the specifics and details of how that works. This is kind of a real super broad, quick overview on how this is going to be used in later chapters as we move on. So my answer to this would be yes, this is a polar molecule because it does have opposite ends. So what about some other examples here? Let's actually skip past this one. Let's use something like, here we go. Let's say we have carbon disulfide. So we have something like this is our formula, and if we were to draw this out, and we would have carbon as our central atom, and each sulfur needs 2 valence electrons, and so we're going to form a double bond with the sulfur, or to each sulfur. And so there I've got my bonds drawn, and these little sulfurs here, if I want to draw on my dot structure there, those are nice and happy and good. And we've got our carbon in the center here. And so now what I need to figure out is, here's my 2 bonds. I've got my 2 double bonds, and I need to figure out which one, or actually as I look at each of them, first of all, is it a polar bond? And then I need to figure out which direction is it shifting. In this case, I'm going to compare carbon and sulfur in terms of their electronegativity. And they are fairly close together, so there's not going to be a whole lot of shifting. But sulfur is slightly stronger. It may have been better if I used oxygen or something like that. But let's say sulfur is slightly stronger than carbon. And so the electrons in this bond are going to shift this direction in this bond because sulfur is stronger. And in this bond over here, the electrons are going to shift this way towards sulfur. And so what I end up with then, as I'm looking at this is a linear shape. And on this end, because the electrons shifted towards sulfur, sulfur would in essence be negative on this end, and it would be negative on this end. And as I look at it, I have a negative on this end here, and a negative on this end here. And as a result, because I have negatives on either end, this is what we would call non-polar, because they're not opposite ends. In order to have a polar molecule, I have to have opposite ends. One end has to be positive and the other end has to be negative. And since these are what we call, let me erase all of this here, since this is what we call symmetrical, in other words, you have a negative here, a negative here, they're both the same element. The electrons are shifting to create a negative charge on both ends. Then you have what we call a symmetrical molecule, and it is non-polar in this situation because I don't have opposite charges. Now, if we had something else here, if I had, let's say, a hydrogen attached, or something else that had a weaker electronegativity than carbon, and the electrons were shifting away from it, and it had a positive and sulfur had a negative, then we would end up with a polar molecule. But this one would be what we call non-polar. Let's take a look at something else. Okay, let's do this guy right here. Let's say we have something like fluorine and iodine bonded to each other. So you have fluorine, and it's going to form a single bond with iodine, and each of these guys has their 7 valence electrons here. And so we have this single bond here, and again, it's the bond that we're focusing in on, that we're taking a look at, and that's what it's important to us. And as I take a look at this bond here, I want to take a look at which of these two is stronger. And in this case, fluorine is stronger. It has the higher electronegativity, so my valence electrons are going to shift towards fluorine and away from iodine in this particular molecule. So what would that mean? It would mean this, real simply, that fluorine ends up with a negative charge, and because those electrons shift away from iodine, iodine ends up with a slightly positive charge. And so as I look at this molecule, do I have opposite ends? Yes, I do, so therefore it's what we call a polar molecule. Okay, so that's what you're looking for, and again, you're just looking for where they shift, and do my ends end up being positive or negative. That's what we call a polar molecule. And we will continue and do some practice with this further in class, but that's the basic concept behind what is a polar molecule and polar bonds.